a radar blip, a thermal streak, and a satellite frame. 3 different instruments all pointing to the same impossible motion. Not a viral clip, not an eyewitness claim, but raw signals aligning across platforms. By 2026, those fingerprints are no longer only the stuff of late-night forums. They show up in pilot logs, on military dashboards, and in declassified briefings. Tonight we cut through the noise. We'll show what's actually new, what still doesn't add up, and the few things that could change everything about UFO mysteries over the next year. Quick note before we dive in, unidentified means unidentified. Most sightings will have ordinary explanations: glitches, birds, balloons, or space junk. That's normal. The handful that survive rigorous, multidisciplinary scrutiny teach us about both the objects and the limits of our sensors. If you want answers, the first rule is simple: follow the raw data. Number 1, multi-sensor confirmation. The single most persuasive incidents are the ones where independent systems, radar, electro-optical, and infrared cameras and satellites all record the same object at the same moment. Why does that matter? Because it moves the story off eyewitness testimony and edited clips and onto measurable signals. When raw radar returns, full-rate infrared files and uncompressed satellite frames are released with accurate timestamps and metadata. Independent analysts can reproduce tracks, rule out artifacts, and test alternative explanations. Think about it like this: one sensor can be fooled. A camera can pick up a reflection, a radar can register a flock of birds or a processing artifact, but 3 independently designed systems with different operating principles and different failure modes, agreeing on position and motion at the same time. That's a very different problem. The 2004 naval encounters in the public record are often referenced because pilots, radar operators, and shipboard systems documented anomalous behavior. Those cases sparked the modern push for data transparency for a reason. In 2026, watch for incidents that include those unprocessed streams. That's when the debate shifts from someone saw something to multiple instruments recorded the same something. Number 2, anomalous motion and transmedium claims. Over the last decade, a small number of reports described objects diving straight into the sea, vanishing and reappearing, or accelerating in ways that exceed known aircraft performance. Those descriptions force 2 competing explanations. Either we're looking at genuinely new capabilities, or we're misreading sensors and the processed outputs they produce. The difference comes down to provenance, where the signal originated, how it was processed, and whether the timestamps and processing logs survive. Real science is messy but repeatable. If radar waveforms with full timestamps and signal processing logs match optical tracks, then you have a problem that demands new hypotheses. If the supposed maneuvers only appear after filtering, smoothing, or selective clipping, odds are you're seeing multipath reflections, algorithmic artifacts, or parallax-induced illusions. The most consequential cases will be the ones where unprocessed time-synchronized streams survive long enough for independent groups to try and fail to reproduce a conventional explanation. That's the point where mystery becomes an anomaly worth focused study. Number 3, commercial space. The explosion of small satellites imaging Earth changes the game in both directions. On one hand, thousands of satellites mean more cameras pointed at the sky and more chances to capture a fleeting event. On the other hand, that volume multiplies glints, sensor quirks, and confusing metadata. A cropped promotional image can be compelling to a viewer, but it is practically useless to a scientist trying to reproduce a track. The important development to watch is whether Earth observation companies decide to make full frames, calibration data, and precise orbital metadata available for anomalous events. When firms like Planet and Maxar and the growing constellation operators provide unredacted frames and timestamps to independent scientists, we stop arguing over cropped clips and start doing real forensic work. Full frames let analysts check surrounding pixels for reflections, cosmic rays, or other confounders. Calibration data reveals how the sensor responds under different illumination. Precise orbital metadata tells you whether that satellite's viewing angle could have produced a parallax error. If commercial operators withhold this material or only supply promotional clips, the debate will stay stuck on contested footage. If they open their vaults, the field shifts from speculation to reproducibility. Number 4, international contributions. This is not just one country's problem. Aviation authorities and military services from Chile to Japan to Brazil hold encounter logs and archives that are largely underused. Those records are valuable because different nations use different sensor suites, different airspace monitoring techniques, and different documentation practices. Cross-border cases where complementary sensors from neighboring countries capture parts of the same event are especially valuable because they reduce single-system biases and offer multiple viewpoints. Imagine a coastline incident where a naval radar, a commercial airliner's TCAS, and a regional weather radar in another country each record aspects of the same object. Each system will have unique metadata and known limitations. Together, they can close gaps in understanding. In the year ahead, the most credible openings for scientific progress will come from multinational releases or cooperative statements where raw data can be jointly examined. Science is international. Anomalies that survive scrutiny from diverse technical cultures are the ones that deserve concentrated attention. Number 5. New analysis tools. Machine learning, open source signal processing, and modern statistical methods aren't magic. They are powerful amplifiers when fed good data. Automated clustering can reveal repeatable signatures across years of tracks, showing patterns human analysts might miss. Sophisticated waveform analysis can separate true transients from radar clutter. Open source toolchains let independent teams reproduce results rather than trust single labs. But there's a catch. Algorithms can only help if datasets exist for training and validation. You can't train a neural net on cropped clips or promotional reels. You need full raw streams, labeled examples, and clear documentation of how the data were collected and processed. Expect the biggest breakthroughs to come from teams that pair novel methods with transparent, well-documented input data and make both the code and the data available to others. So what would actually change everything in the next year? It won't be a single dramatic event on its own. Real progress requires a stack, a combination of elements that together create a reproducible, irrefutable anomaly. First, time synchronized raw sensor streams from multiple platforms. Second, unambiguous cross-validation by independent analysts using openly available toolchains. Third, a willingness from governments and commercial operators to open their logs and frames to the scientific community. If that stack appears, a clearly recorded reproducible phenomenon that resists known explanations even after exhaustive cross-checks, the conversation will move from anecdote to anomaly to a legitimate scientific problem worthy of concentrated study. There are a few realistic outcomes that would mark real progress. 1. A multinational dataset where shipboard radar, airborne FLIR, and at least one satellite frame align exactly in space and time, and independent teams fail to explain the motion with conventional physics or sensor error. 2. A commercial operator releasing full calibration data and unredacted frames for a high-profile event, enabling outside groups to reproduce or refute an extraordinary claim. 3. The emergence of open-vetted toolchains that let researchers, journalists, and citizen scientists apply the same analysis methods and reach the same conclusions. If those things happen, the field moves forward. If they don't, we're stuck in the same loop, dramatic clips driving headlines, followed by competing claims and no resolution. Transparency is the fulcrum, so what can you do? First, demand transparency from agencies and companies. Ask for raw frames, precise timestamps, and full signal logs, not polished clips. Those are not technical niceties. They are the difference between a puzzle and a parlor trick. Second, support independent analysis by sharing verified information with researchers rather than reposting edited footage. Third, if you work in aviation, defense, or remote sensing, preserve and document raw data. Proper archiving changes everything. And finally, follow the evidence as it develops. Subscribe, turn on notifications, and pay attention when credible datasets are released and independently reanalyzed. We're at a moment when more sensors, better tools, and a bit of institutional courage could finally turn mystery into data. The sky has always been full of questions, for decades. Curious aircrew, engineers, and scientists have kept meticulous records for good reasons. The answers are rarely simple, but they are discoverable if the data survive. With the right evidence and the right attitude, openness, reproducibility, and hard skepticism applied evenly, we might at last begin to answer some of those questions. If you want to help demand the data, insist on timestamps and metadata. Share verified sources with researchers, and when credible, well-documented datasets appear, pay attention to the analysis, not the headline. The difference between rumor and discovery is not drama. It's raw signal, preserved and examined. Keep watching, keep asking for the data. When the stack comes together, the sky will give us far more than a story. It will give us a problem we can solve. Subscribe and turn on notifications to be the first to see that evidence when it's released and independently reanalyzed.